Hi everyone. Today let's talk about session 7.2, interval estimation. So last time we talked about point estimation. We used the sample mean to approximate the population mean. We also have the error bound. Okay, we know the error bound with probability 1 minus alpha is E equals to Z alpha over 2 times sigma over square root of n. And also depending on the sample size and whether we know the population standard deviation, sometimes we might need to switch to the t-distribution. Okay, so today we're going to talk about interval estimation. So since point estimates cannot really be expected to coincide with the quantities they are intended to estimate, replace them with interval estimate. So suppose now we have a large random sample. Large means greater or equal to 30. Okay, then we use the standard normal distribution to calculate. Okay. And suppose we know the variance, the population variance sigma square, then we know that the standardized sample mean is approximately normal. Okay, so last time, what did we talk about? Okay, last time we talked about, here we have the sample mean, okay, and now we know the error bound. The error bound is like E. Then this is like x plus E. This is x bar minus E. Then we know our mu. We have probability 1 minus alpha, such that the population mean will lie in this range. Okay, so actually this range is the confidence interval. Okay, so here is the algebra. 1 minus alpha equals to the probability of the z lies between z alpha over 2 and minus z alpha over 2. Okay, so the picture is like we have 0 here, and this guy is 1 minus alpha, the probability. Then this is z alpha over 2. This is minus z alpha over 2. Okay, and then it's the same as the we multiply both sides by sigma over square root of n, and this is our error bound E, right? And what does that mean? Well, it means that the mu, okay, if we get rid of the absolute value, then we can get x bar minus mu is bounded between E and minus E, right? And here we can subtract x bar on each of the term. Subtracting a number won't change the inequality, okay? And then when we divide it by minus 1, it will change the inequality. So when we divide it by minus 1, the left guy becomes z alpha over 2 times sigma over square root of n. Multiplied by minus 1, so plus x bar. It flipped the inequality, so it becomes plus bigger equal to mu, greater equal to minus z alpha over 2 times sigma over square root of n plus x bar. And we just reorder, just put this guy on to the left and put this guy on the right. Then we have the inequality flip. Okay, but they're the same thing. It just means that instead of getting just a point, now we have an interval. So then we have like 1 minus alpha times 100% confidence that our population mean will lie in this interval. Okay, so this concludes the following. First case, large sample confidence interval for mu if we know sigma. Well, that is the sample mean minus the error bound, okay, and the sample mean plus the error bound, right? So we can say with 1 minus alpha 100% confidence. Do you have a question like why do we put 100% confidence there? Remember, usually we say probability with probability 0.95, and then we say 95% confidence. So that's why if we use probability 1 minus alpha, then how many confidence? It's 1 minus alpha. So 1 minus alpha is like 0.95. You're going to multiply by 100% confidence, so it becomes 95%. That's why there is a 100% right here. Okay, so we can say with 1 minus alpha, 100% confidence that the interval contains mu. We call this interval a confidence interval, so we use CI from now on to denote that. Okay, having the degree of confidence 1 minus alpha, or we can say 1 minus alpha times 100%. And its endpoints are the confidence limit. So far, so good, everybody? Okay, so it's very similar to what we learned before, but now you just, instead of getting a point, we take into account the error bound so that we get a range, an interval for it. Okay, example 1. A random sample of size n is 100 is taken from a population with sigma equals 5.1. Given the sample mean is x bar equals to 21.6, construct a 95% confidence interval for the population mean mu. Okay, so here, 95% confidence, well, that's the same as 0.95, right? So that's 1 minus alpha, then alpha is 0.05. Alpha over 2 is 0.025. Okay, so here, because we have large sample and we know sigma, so we use Z, standard normal distribution, to calculate. And Z 0.025 is, let's look at our T table, the last one. So alpha is 0.025. So 1.96. So this is 1.96. So far, so good, everybody? Okay, this is by table 4, the last row. Okay, the Z alpha values. And then by the formula, okay, by the formula of the confidence interval. Okay, so by confidence interval formula, we get x bar. What's x bar? 21.6 minus Z alpha over 2, which is 1.96, times sigma is 5.1 over square root of n, which is 100, less than equal to mu, less than equal to same thing on the left, but replace minus by plus. Okay, let's plug this in our calculator. 21. So everybody, yes, please work on this problem with me. So let's put this in our calculator. You can always pause the video and try the problem first. And then once you're done, we can check our answer together. So I got 20.6004. And on the right hand side, you don't need to type the whole thing again. You just go up to your previous formula and then replace minus by plus. Okay, I got 22.5996. So far, so good. Yeah, so we answered the problem by the 95% confidence interval is 20.6004, 22.5996. Okay, so this is how we answer the problem. So far, so good, everybody? Okay, let's continue. Second case, what if we don't know sigma? We don't know the population standard deviation. Then we use the sample standard deviation to approximate it. Okay, so formulas almost the same, just replace sigma by S. Okay, so let's look at example 2. A random sample of size 50. So 50 is n. 50 is large, right? It's larger than 30, then it's large. Okay, and then we have a population, a sample population. We have the sample mean is 305.58. The sample variance is 1366.86. Construct a 99% confidence interval for the population mean. So I hope all of you can pause here and try first. Are you done? Let's go over it. Okay, so 99%. So it's 0.99. That is 1 minus alpha. What is alpha? 0.01. Then what is alpha over 2? 0.005. So far, so good, everybody? Okay, then what is, so here we still have large sample, so we still use z. So z 0.005 equals, let's look at table 4. Alpha 0.005, so the last column, 2.576. Okay, so we can put in x bar is 305.58 minus z alpha over 2, which is 2.576 s. By the way, here we have s squared. So what's s? Square root of 1366.86. You gotta be careful sometimes if we're given the variance. To find the standard deviation, you have to take the square root of the variance. And then square root of n, which is 50. Okay, and then the right hand side is the same thing, but we place minus by plus. Okay, so let's plot this in our calculator. 305.58 minus 2.576 times square root 1366.86 divided by 50. Okay, I get 292.111387. So this we round up 4. Okay, mu, and the right hand side we just go up to that row and then change the minus to plus. You don't need to type the whole thing again. You can always go up to your calculator, choose the previous formula you input, and then change the sign there. So I get 319.0486. 1. The next digit is 1, so we don't round up, we round down. Okay. So then we answer the 99% confidence interval is 292.1114, and this is 319.0486. So far, so good, everybody? Okay, good. So, by the way, you know, t distribution and the standard normal distribution, they are all continuous distribution. So for the confidence interval, you put branded parentheses or brackets, doesn't matter. Okay, the probability of a single point is 0. Okay, so if sigma is unknown and n is small, but the population is normal, then we have the third case. Okay, so we have a small sample, and we know the population is normal, but we don't know the population standard deviation. We use the sample standard deviation to approximate it. So what's gonna change? We have s, and we use t instead of z. Okay, example 3. The mean weight loss of 16 grinding balls after a certain length of time in meal slurry is 3.42 grams with a standard deviation of 0.68 grams. Construct a 99% confidence interval for the true mean weight loss of such balls under the stated conditions. Okay, so n is 16. 16 is small, right? It's less than 30, so it's small. And this is x bar is 3.42 with a standard deviation, so that is s. Okay, so 99% confidence. Well, 1 minus alpha is 0.99, alpha is 0.01, alpha over 2 is 0.005. Here we use T, so T 0.005. What is degree of freedom? Is that 16? No, 16 minus 1, which is 15. Okay, degree of freedom is n minus 1. Oops. Okay. So be careful. Let's look at our T table. Degree of freedom is 15 and 0.00005. Oh, 2.947. So 2.947. So far, so good, everybody? Okay, let's plug in our formula. X bar is 3.42 minus T is 2.947 times S is 0.68 over square root of n, so square root of 16, less than equal to mu, less than equal to the same thing on the left, but plus. Okay, so let's plug this in our calculator. 3.42 minus 2.947 times 0.68 divided by what square root of 16? That's 4, right? Okay, my answer is 2.91901. Okay, less than equal to mu, less than equal to, let's see, we placed minus by plus in the previous formula. So 3.92099. Okay, so that is our confidence interval. So the 99% confidence interval is 2.91901, 3.92099. So far, so good, everybody? Yes, so this is our confidence interval. Do you have the same answer? Okay, let's talk about some remark. First, before the observations are made, X bar, the sample mean, and the sample standard deviation, they are random variables. So the interval is a random interval. It is centered at the sample mean with its length proportional to the standard deviation. This is a sample standard deviation. So this interval will cover the true mean mu, which is a fixed value, with probability 1 minus alpha. Remember, before we observe the values, we talk about probability statements, okay? And 2, after the observation are made, we have small x bar and small s. They are numerical values. They are fixed numbers. Then the interval x bar minus t alpha over 2 times s over square root of n. So this interval is a fixed interval. Then we have 1 minus alpha. 1 minus alpha times 100% confidence. That this interval, this is fixed interval, will cover the true mean. Okay, so this is the difference between probability statements and the confidence statements. For example, if we perform a lot of experiments and calculate data, then we get the number of intervals that cover the true mean over the number of intervals we calculate is close to 0.95. So this is what it means by saying, oh, okay, we have 95% confidence that this will cover the true mean. Okay, it's the ratio of the number of intervals that cover the true mean over the number of intervals we calculate is close to 0.95. It's like the law of large number in chapter 6. We talk about that example. We use Sn over n. Okay, remember the example in chapter 6, 6.1, 6.2? Okay, we have Sn over n. When n goes to infinity, this get close to p. Okay, where Sn denotes the number of success. Thus, we repeat the procedure for many times. About 95% of the confidence we calculated should cover the true mean. Okay, so that is the probability statements and the confidence statements. So conclusion. For large n and sigma known, then the confidence interval is this, okay, which I already included in the table in the previous session, but we cross out and say we're going to talk about that in this session, okay, but I already included in the previous session. Okay, second case, if we have a large n and we don't know sigma, then we use the sample standard deviation to calculate. Okay, so we place sigma by s. We still use z because we have a large sample. But if we have a small sample and we don't know sigma, and also add the assumption that the population is normal, then we'll use t distribution to calculate. And the degree of freedom is n-1, it's not n. So I emphasize many times, so I hope that you won't make this mistake. Okay. So that is session 7.2. Yeah, that's quite short. See you.